Our next speaker is Andrew Ellis with Oxford Instruments, and his topic is the Exmet Handheld X-ray Fluorescence Analyzers, a Stainless History. Andrew?
So good afternoon, and thank you very much for the invitation to speak today. I'm going to take you back a little bit further in time and a different route by which people arrived at handheld XRF analyzers in Finland over the years. And I'm going to do that on the backdrop of stainless steel. It's been a rather challenging application which XRF, and particularly handheld XRF, has proven itself extremely capable in. So let's go right back to the beginning of stainless steel. I come from Sheffield in England, as did Harry Brearley, and around 1912, 1913, he recognized, along with many others, that the addition of chromium to conventional steels in high levels rendered them unoxidizable, even when scratched. It was quite a tremendous development program to industrialize that material rather quickly, particularly for military equipment. Unknown to Brearley at the time, in Germany also, Strauss and Maurer were also patenting austenitic stainless steel that we all know and love nowadays. The original Brearley steel was in fact martensitic and derived principally in Sheffield for its cutlery, and as a consequence was developed very quickly there. The same martensitic grade of stainless simultaneously was being developed by Elwood Haynes here in Pittsburgh, and to connect us back to the conference. And he applied for a patent at that time, so in three major steel areas of the world, stainless steel was actually happening. They didn't know much about that between them, and it wasn't until 1915 when the New York Times came along and reminded people that actually this new material was available. And it began, despite slow communication, to get communicated around the world as a great material. At that time, the Swedes, Avesta in Sweden, said, yep, we'd like to get into that. We've got a lot of natural resources. And as a consequence, they took a license out for the original stainless steel patent, which had been developed in Sheffield. So stainless steel hit the main three areas of industrial steel, as it were, at the time, and it began to move towards Finland. And why is that? Well, the Finnish connection that I'm going to take you through is that of Outukumpu, a company which was founded in 1910 and named after an Outukumpu, which is a strange mound, under which happened to be a really huge and profitable deposit of copper ore. So Outukumpu developed huge amount of copper, huge amount of mining and processing, and was really a great national strength for Finland. But over that period, it has built its stainless steel capabilities, and in fact divested its copper capabilities in the last decade or so in favor of stainless steel. But why is that? Well, actually there's locally mined chrome ore in Kemi, which is but a few kilometers from the Tornio plant, right up on the Swedish-Finland border in the north. It's actually the only chrome ore mine in Europe. So there's tremendous activity there. Got excellent sea access. Yes, of course, the Gulf of Bosnia freezes over, but that doesn't bother the Finns. They can bring material in and take material out, even though there's a meter of ice all over the sea in winter. So brings in material and takes out material. In addition to that, Outukumpu, like Finland itself, has a very skilled and a strong workforce, and is very committed to science and technology. So this is a good background for its stainless steel growth, in addition to which it's acquired and merged with a number of companies. Avesta originally was taken over into British Steel in 1991, which was then subsequently acquired into Outukumpu in 2001, and only at the end of January this year, 2012, has now the stainless interests of ThyssenKrupp have now been organized into and merged with the Outukumpu business. So that's taken us into Finland. Well, what about the analytical challenges of stainless steel? Because there are actually many. And for metal production, where you've got to get material through the process very efficiently, it's absolutely important for production that you know what you're making, because once you've made it, it's a lot of scrap. There's also the alloy performance has to be right, and stainless is quite complex. So I'm going to take you back to the 50s and 70s, a time when instrumentation was dramatically building up. But through all prior history, wet chemistry had been the main driver for the steel industries. Many, many different ways of digesting and separating material, and ranks of steel chemists working highly skilled to get analysis back quickly and to ensure that compositions were correct. In 63, atomic absorption spectrometry came from Alan Walsh in Australia, and that was heralded as really quite a great way of working. However, it still required digestion, was generally a single element technique, and had a narrow analytical range. Technique which had been in extreme use for quite some time was in fact the hallmark of the steel industry right through the early part of the 20th century, was arc spark optical emission. Tremendous technique which had been developed right back from the time in 1873 when Sir Joseph Lockyer originally identified that when a high voltage arc was drawn, the intensity could tell you not only elements but also their composition. So really put into the business of iron and steel. However, it suffered from tremendous matrix effects. The spectrometers were often huge. 3-meter spectrometers were not unusual. And the complexity of operating them and taking photographic plates meant their analytical skills were still required. Massive inaccuracies on occasion, and the precision was seldom better than a few percent. Coming on to the end of, the 1940s, 48, Burks developed a wavelength dispersive XRF spectrometer. This was the first time a machine which really began to be useful as a new technique for these particularly difficult metals. No longer did you have to digest it. You hadn't had to digest it with optical emission spectra either, but perfect technique for solids and generating extremely good precision where previously that had not existed. Of course, the inductively coupled plasma came through in the early 60s from Stan Greenfield in Birmingham, another steel town, and Velma Fassel here in the US, but generally couldn't work with solids unless they had been digested previously. So these were the techniques that were around at the time. And of course, Outukumpu, as any steelworks, was interested in making them work for their own operation. And it's on that backdrop that the Exmet was really born. It was born by Outukumpu's own Institute of Physics as a major operation, and it was really portable. XRF machines were regarded as huge, easily the size of this table and weighing substantially more than 4 of us put together. It was about 10 kilos, and in terms of its XRF system, it did have radioisotopes. They happened to be extremely small, and you could use any one of 4 very conveniently for the elements of interest. There were multiple heads for multiple applications because radioisotopes are rather specific. And the detector, silicon pin diodes had not arrived then, but gas proportional counters were developed very heavily by Heikki Sipilä, who's been involved right through development of gas proportional counters in X-ray spectrometry and in fact in space exploration. The energy resolution, a little bit better than the original pins of Alan Huber as reported shortly ago, but not much better. It required a huge amount of empirical calibration to make them work for the applications. But my bellwether, if you like, for the performance that we'll go through is that of nickel in 304 stainless at about 10%. The standard error of 0.5% was particularly attractive, but more so was the precision, and only in 60 seconds, and on site. Not a particularly convenient setup, as you see. It required a physicist generally to operate it. But it soon grew up, and by 1984, the 840 came along, still with a portable configuration like this, multiple heads for each different application, but now with electronics that could do much more, multi-channel analyzers in which you could do much more application. Weighed in total about 8.5 kilos, and in terms of its XRF characteristics, was the same as before, but look, modern electronics begin to kick in. You could actually load things and keep them on there. Your calibration didn't have to be made on the day. In terms of performance, the same fundamental performance was still available, so it wasn't changing technically at that stage. However, Finnish ingenuity said, well, you can take this around. It's not portable in the same sense that Lee has just described, but that doesn't stop the Finns. They're quite happy to take it into the forest in a backpack and actually could demonstrate laboratory performance for some applications out in the forest and could even calibrate on site with this equipment at the time. It was fine in stainless steel scrap as well. Here you see the handheld probe, the handheld unit, which has got the isotope in it. And here's the electronics box. It's pretty heavy, but you can manage it. You have to manage it for 10 hours because it's got quite a sizable battery in there as well. Incredibly robust. A company that's based in Finland knows you've got to be able to work with it outside at minus 25. And if you're in the hot end of the steelworks, you need it to be working when it's hot as well. So this was incredibly rugged and truly handheld and quantitative. In 1988, still with Outukumpu, this head now has got two sources in it, so it can do even more, and it's now got better electronics. Still the same basics. Don't forget we're still dealing with a detector here, which is a proportional gas counter, so as a lot of method development has to go into this kind of product in order to get real data out. Getting 6 elements simultaneously from spectra which you cannot discriminate one atomic number from the next is incredibly difficult, but it is possible. It takes a lot of empirical calibrations, and if you want to do really good work, you need a lot of them, and this one said, okay, we need 32 on board now. So electronics are playing the part, but still the performance is not improving much, although the measurement time is actually halved now. So we're beginning to recognize that speed is important as well as portability. At that time, 1994, Metorex was formed out of Outukumpu. It left its original home, and it was a management buyout. And the key people out of that, Erkki Kiuru for the electronic systems, Heikki Sipilä for his detector skills. And it was at this time also, having been working on detectors for so long, their first silicon pin diode was brought out. It had an energy resolution of around about 290, dramatically better than the proportional counters. And it had something called fundamental parameter calculations, which we'll come back to very briefly later on. But this was still portable, not handheld. The handheld probe worked successfully. But now we could do quite extensive grade ID with it, so it really was morphing into a stainless machine to go out and work on the plant. And it now was taking only 15 seconds. And in general, the standard error had now come down from 0.5 to 0.3, which is pretty impressive. Extremely good calibrations were set up for it, but in general needing a lot of standards and a lot of skilled operation, but much easier spectroscopy as a result of the new detector, which was developed in-house by the same team who had been developing proportional counters for the prior 20 years or so, and continued to develop this kind of detector. Then in 2002, Maciej Vasti and John Landerfeld in Keymaster decided to get together, pool their resources, and brought out their first handheld single unit, in which again there was a new innovation, which was an X-ray tube. It was now a single unit. It was truly handheld at 2.2 kilos, and it had a 40 kV tube straight away, and a pin diode which, again, as we saw from Lee's graph, continued to improve. And the count rates were about twice that which were realistically available from the original Exmet with its proportional counter. So what did that do for results? Well, it got us down with a standard deviation now down to 0.15, really making good quality measurements. And for the first time now, in 2004 with the tube excitation, the fundamental parameters calculations were also added in to reduce the number of standards available for real-life analysis. So, shortly after that, 2004, the Metorex company was acquired by Oxford Instruments, who set about creating a new platform with their own X-ray tube and a piece of technology in the FET, the first part of the amplification system, which had been patented and used extensively on silicon lithium devices, proved equally effective on the pin diodes, and in general reduced the working energy resolution down to 190. So it was now a spectrometer that worked really rather well. Standard errors down to 0.25, and standard deviation now reduced yet again, not only down to 0.1, but now in 10 seconds or less measurement times. And with fundamental parameters, more computing power on board, we're able to get the standard error for alloys FP, for stainless steel particularly, down to about 0.25%, which is quite a big step. It morphed along. 2009, as we heard a moment ago, the introduction of the silicon drift detector really transforms in two ways. It transforms it on the basis of a much better energy resolution, much sharper peaks, better spectroscopy, but also the count rate. Something we were always told in energy dispersive XRF you can't have is sharper peaks and greater intensities. The drift detector's done both simultaneously, and that truly is a step in the right direction. In addition, the improvements that we're now seeing in X-ray tubes, higher kV, and better sensitivity for light elements, in particular now bringing our standard deviations down to 0.05. It's an order of magnitude better than they were at the beginning of the Exmet's life, with an order of magnitude improvement would basically, it's just huge in terms of precision. It requires 100-fold improvement, really, in counting error. Can now go down to magnesium, and limits of detection of magnesium in a very difficult spectrum in aluminum were achieved at 0.25%, but in air. The simplicity of the Finn's approach to it said, don't use helium, don't use vacuum, let's just do some neat optics and correct for barometric pressure. So perfectly capable of doing this in air. And in general, the time is again coming down quite nicely. Bringing us right up to date. The internals of the product much the same, but this is a field product. The ruggedness that was in the original Xmets of going out into the field has got to be brought in with these somewhat more fragile technologies of newer detectors and X-ray tubes. They're not fragile in the normal sense of the word, but when they're going out in the field every day, working hour after hour, these things have to be ruggedized. They also deliver performance. So this is the kind of performance you get out on the site. And as Lee pointed out just a few minutes ago, to deliver that kind of capability in a handheld device was unthinkable 20 or 30 years ago. And it's fantastic that the technologies have come through and the people behind them, particularly the detectors in this case. We've mentioned Alan Huber, and the drift detectors developed primarily by Kemet and his group in Germany. And a number of real big developments in pin diodes came out of Heikki Sipilä's team also. So let's just review the milestones. The detector has really dramatically got better. That allows much better spectroscopy, as we'll see in a moment. But let's not forget the nucleonics. We talk about detectors, but a detector is no good without its amplification and multi-channel system. And when you can get count rates going up at the same time as getting better energy resolution, it's just fantastic for X-ray spectrometry, and we'll continue to develop in that way. To have them both going in the correct direction has allowed spectrometers to do things which were just not possible in that format some 15 years ago. Also with excitation, we've talked about moving from radioisotopes, the unacceptability of those in many ways, but there are a lot of benefits, up to 45, 50, 55 kV tubes with different window configurations allow us to get to a lot more applications, not just metals, but I'm focusing on stainless steel in this talk. So what about energy resolution? Alan, I'm sure, will tell us much more about it, but this is typical spectrum of an 1810 stainless steel. Iron, K alpha and K beta. The chromium and the nickel, they're pretty well resolved. In fact, in the drift detector here, they're extremely well resolved. We're about 100 EV better than we were 10 years ago with the Penn diode. Much better overall spectroscopy. But in this example, about 13 times the counts, which gives us a precision improvement straight away of about 3.5 times. And that kind of improvement from a single technology step is really making new applications and better analysis for stainless steels available in a handheld system. In excitation, originally isotopes were used. Well, why? Well, actually, they're tremendously compact. really small, the size of a thimble, the end of your finger. Yes, they need some shielding, but that doesn't make them much bigger. They require no power. And for a system that's going to go out and work on a battery for the whole day, that's a big benefit. And they actually have real advantages in some applications where those specific lines, let's say from an IM55 spectrum at 5.9 keV, they can be particularly effective. However, they're generally weak unless you're brave and you want a very big source in there. And they all pretty much decay. Cadmium 109 and IM55 in particular, which are the favorites for stainless steel analysis, they're also always on and radioactive. People don't like them. So X-ray tubes come along, they have a much more intense output, much more intense, and they're highly flexible. Spectrum down here shows the output spectrum KV along here of 3 different filters. And you can see the quite different shape of the excitation spectrum that you can gain by the simple use of beam filters. So very intense, but they require power. So that's a problem if you're going to have to use one out in the field for 10 hours. You need battery packs. You can get those, of course. And its size is bigger, and actually it's more complicated. There's nothing to do with the source. It's just on. An X-ray tube needs electronics and all kinds of stuff around it, not so isotopes. So let's talk about what that all does for accuracy and why it really matters. Well, it matters because specifications are increasingly tight. Nickel and molybdenum, which are key components, key parts of stainless steels nowadays, well, they're expensive, in excess of $20,000 per ton around about at the moment. And matrix effects with these materials are really quite a big challenge, and that limits accuracy in a number of ways. But that's improved all throughout the Exmet lifetime. This little schematic here, rather crude, but it indicates that the emission of iron is here, the emission of nickel is here. But the strongest part of the absorption edge, as it is in XRF spectrometry, sits between the two. And another one sits between chromium and iron. So nickel gets very strongly absorbed by iron and by chromium. And similarly, iron gets absorbed by chromium. And all of these interelement effects mean that if you're to just do a simple calibration, you can readily be 10% inaccurate, and much worse in some cases. So originally, calibrations had a limited number of standards available and tended to cover narrow ranges for that very reason, that these were complex corrections that needed to be made. Empirical corrections really were much better. They came along and allowed these interelement effects to be better reflected mathematically. And in particular, the intensity corrections, first brought out by John Lucas Tooth and Brian Price in the UK and published in Metallurgica around 1962, gave us equations which allowed us to relate these changing intensities from the spectrum to factors which allowed us to correct for those interelement effects. And now, not only could we get high precision, but with good corrections, we could actually extend the analytical range, reduce the number of standards, and get much better performance out of the instrument. Those went into most of these early systems. Computing power, of course, drove improvements in those. And really throughout, I guess, the 80s, people argued about how many more factors needed to go into these to improve accuracy. And then, actually, it was done properly with fundamental parameters, elegant simplicity, reduced really by Sherman in 55 and properly implemented as a set of algorithms in a program at Naval Research Labs by John Criss and Vern Burks in 68. It incorporated all of these complex matrix effects. It's not an easy equation to solve or an easy set of equations, but increased computing power and available memory allowed that to happen. And over the period of time in the Exmet, we've seen from 1998, from those first alloy fundamental parameter calculations, through the use of backscatter into different matrices, and now light element analysis, and indeed multiple conditions added together to give a single unified result. Well, who did it? Well, Russians did it in this case. Oleg on the right and Evgeny on the left. This is when they were really beginning with fundamental parameters, and this is what happens afterwards. They were much wiser afterwards, but they were attacking the problem right from the beginning. They knew that you had to get clean spectra to begin with, so they attacked that first. When tubes came along, they knew that had to be modeled, much more complex than radioisotopes, so they set to and did that as well. Then there are a number of other corrections that needed to happen to make sure the intensities were good, and the thing that then you're trying to solve is the matrix effects, and they did that, incorporating all of the complexities, and that in a tiny low-power computer that fits basically in your hand, and it's got to be fast. Not like it was 15, 20 years previously when people were happy to wait for several minutes for the calculation to complete, which is what it took. It now has to happen with no delay. The overall measurement time is maybe 2 to 3 seconds. So let's recap the history then of the Exmet, which takes us right back 74 and really brings us uphill through a number of quite interesting instrumentation changes, but still relying upon a lot of method development, a lot of people knowing how to take complex data out of really quite simple spectra and making them work in stainless steel. And then true handheld, as we heard a moment ago, kicks in through here, and the performance just continues to get better. So who are the people behind this particular Exmet? Well, it's a story of fins, as we started at the beginning. Way back in Outukumpu, Heikki Sipilä, long known for his work extensively in proportional gas counters, Erkki Kyry in nucleonics. In order to get measurements on site in very compact and difficult environments, you need to spend a lot of time getting the nucleonics right, the first stage of the measurement system. He was particularly skilled at that. Stan Pjorek, you'll meet shortly, was undaunted by the quite difficult spectra that were placed in front of the methods development people and attacked with gusto, as did others, the challenge of getting quantitative analysis out of these machines. In the Metorex times and then Oxford Instruments, this team really drove the Exmet handheld with tube excitation. Erkki Puusaari on the physics, Rita and Kai systems had to be integrated, Veikko Kamarainen, who understood how to improve silicon pin diodes and make them producible and repeatable. Esa Numi again knew how to take spectra which now are much easier to work with, but were being asked to do much more complex applications. And he had also attacked that. So through to the modern day, where we have Outukumpu, and who's now a world leader in stainless. ThyssenKrupp merger is now announced and will go ahead, and they will continue to drive efficiency and their recycling. Currently, they recycle about 90% of stainless steel. The world average is about 60%. And with that level of recycling, analysis and quality control will drive improvements in all instrumentation and in all production processes. So where Outukumpu started out this Exmet trail, they'll see the benefits from that as handheld instrumentation continues to deliver them great analysis for their primary task of stainless steel manufacture and distribution, but also the knock-on effects of that, the mining that they do. Of course, somebody has to take care of material coming out of the mine, know it's up to quality, and the environmental impacts of mining, high power sources, and of large steelworks, again, as demonstrated a few moments ago by Lee, the handheld XRF systems and the Exmet are perfectly at home working with the environmental problem as with the stainless steel product or production processes themselves. The team in Espoo, still based very close to the Outukumpu headquarters, but in its own separate factory, will continue to improve this same basic device, continuing to think about ways of improving the accuracy. Benchtop XRF, as you know, has got much better accuracy in the past few years. It's now filtering down onto the benchtop. Speed and precision will continue to be a challenge. People want results now, and when you can sample regularly, it means that even though you've got intrinsically high precision, you can also eliminate a lot of the sampling errors by working in the field that otherwise you would get in submitting samples to the laboratory. This important factor in handheld XRF is, as was mentioned with environmental sampling, just one day in the field is really worth weeks in a laboratory system to understand where hotspots are and how treatment processes can be carried out to remediate the land itself. Importantly, of course, portability. It's difficult to imagine where in the last 40 years size has really changed and performance has gone up so quickly. Another 15 or 20 years, the development of handheld XRF for sure will continue, and these equipments will get much smaller and retain their fundamental analytical strength of accuracy and precision. They have to be rugged, and because they're getting deployed in such great numbers to people who have no chemical experience particularly, they've got to be usable. They've just got to give the right answer here and now. So with that, I hope I've taken you through a history of the Exmet and derived it really from stainless steel, which remains a very important material, analytically complex, but as demonstrated, I hope you'll see that handheld XRF really is up to that challenge and very many more. Thank you very much for your attention.
We do have some time now. If you have some questions for Randy, now's the time to entertain them. Yes, sir.
I think what you asked was what's happening in the future for detection levels. It's inevitably the improvement in precision. XRF's great. It's really quite predictable. Square root of the number of counts gives you your error in measurement, so it's very easy to establish what will happen to a detection limit given the count rate that can be achieved and also given the amount of overlap. So the silicon drift detector for sure, with its energy resolution in handheld units, certainly less than 150 eV, there's chance for that to improve in practice to give us some further improvement. It's in electron microscopy, microanalysis, we routinely are seeing those detectors offering 122, 125 electron volts. So that's going to continue to improve the raw spectroscopy. And as digital signal processors continue to improve, we'll get the count rate up as well. The output from X-ray tubes, all of those things will drive the count rate. And the energy resolution will improve a little bit. So detection limits will come down yet again, I'm expecting in the next 5 years, at least a factor of 2. And what will happen is that more applications will start getting used, or that this equipment will get used for more applications, where those kind of capabilities then go into where other techniques have been putting out detection limits for many years. And what you'll find, I think, in handheld XRF is the pragmatic detection limits, where when you go out in the field, that's what you really get. It wasn't in pure water, or it wasn't in a matrix that nobody heard of because it was so clean. It'll be in dirt, it'll be in soil, it'll be in scrap. So you'll get what you get. You'll get what you expect.
I believe we still have time for another question if somebody has one. If not, I thank you for your questions. We have about 4 or 5 minutes before we want to continue, so we'll have another pause.